Alright, thanks for watching. And I don't know if you noticed, but we've been talking so much about the real numbers, but we actually never defined what a real number is. But not anymore, because today we'll construct the real numbers. But just be warned, this might change the way you think about real numbers. So it's pretty freaky. Okay. So again, you're in 5,000 years ago, you don't know what a real number is. The question is, how would you define square root of 2 without ever mentioning the number square root of 2? Without, let's say, writing square root of 2. Because, remember, real numbers, we don't know what they are yet. Our universe is just all the rational numbers. And of course, I know you can define it as r squared equals 2, but we want to generalize this to any real number. And it's quite clever in some sense. In other words, consider the following set. So note, let S be the set of all rational numbers that are smaller than square root of 2. So again, here's what you have to think of. We have square root of 2 here, which again, we don't know what this is, but we definitely know all the rational numbers before that. So we know what rational numbers are. In particular, what this is just a set of rational numbers. So for instance, what's in it? Minus 3 is in it. I don't know, minus 1.5. 0 is in it. 1, but also let's say 4/7. And then 1.4, ... Now, ignore this definition for a second. To the naked eye, this is just a random set of rational numbers. So this, we know what they are. Just a bunch of rational numbers put together. And it turns out this is the definition of the real numbers. It's just some very specific set of rational numbers. So again, a real number is just a set of rational numbers. Whoa, right? Definition, a real number, again, to specify that those are sets, we write capital S, is a subset of the rational numbers such that the following three things hold. So such that the following three things hold, and this is sometimes called a cut, or a Dedekind cut. Which I love that name, it reminds me of King Dedede in Kirby's Dreamland. So, such that the following three things hold. All of, by definition, a cut is not empty, and it's not all the rational numbers. So again, we declare it to be that way. And then there's a very interesting property now, namely, suppose, let's say R is in S, and S is less than R, so S is a rational number, with S is less than R. So again, suppose again R is some element in S, and S is, again, doesn't have to be an element of S. It's just any random rational number smaller than R, then automatically S is also in our set. In other words, what is this saying? It says simply that our set S contains all the rational numbers before R. So this is if you want your set S. So in other words, it's negative infinite from one side, if you like. And moreover, S has no maximum in the following sense. So no matter which number in S I give you, so if R is in S, so again this is R, that's in S, you can always find some element in S that's bigger than R. Then there is S in S with S is bigger than R. Okay, so yes. Now, in other words, again, this says this has no maximum. For instance, one case we would not hold if, let's say, R is the biggest value of S, then there is no S in S that's bigger than R. So what we're saying is essentially S doesn't have an endpoint in some sense. And also be very careful. So I know those two things, 2 and 3, seem to say the same thing, but they don't, because what we're saying here is that for every rational number, S is less than R, but here we say there is an element of S that is bigger than R. So one is a for all statement, the other one is an existence statement. So very, very subtle difference. Okay, good. And now for the couple of minutes, let me do a couple of examples of cuts and not cuts, so you can really see what's going on. The first one is very important and similar to the square root of 2 example I talked about. So important example. First of all, if A is a rational number, again we know rational numbers exist, that's good, then can define the following set. S, sometimes called A star, and it's simply all the rational numbers less than A. Okay. So again, given a rational number A, let S simply be all the rational numbers less than A. And you can show that this is a cut. Because, okay, it's not empty, it's not all of Q, but also, you see, it's sort of semi-infinite from below, and also it doesn't have a maximum element because we have a less than. And those sets of the form rational numbers less than another rational numbers, that's what's called a rational cut. And in particular, what is that saying? It says that given a rational number, you can define a cut like that. So just concretely, what would 1 star be? So 1 star is again all the rational numbers strictly less than 1. So again, this is 1, and that's 1 star. Includes 1/2, 0, minus 9001, or anything you want. And in particular, again, what this is saying is, given a rational number, we can define such a real number, 1 star, for instance. So in this sense, we can say that the rational numbers are included in the real numbers. Because given a rational number, we can naturally define a real number in this way. Okay, so that was an example of a cut. Now the question is, what are examples of non-cuts? So for instance, of course, the empty set is not a cut, and the rational numbers are not cuts. Simply by the definition, we assumed cuts are not empty and not the rational numbers. Another non-example is anything that's sort of not infinite. For instance, the set of rational numbers between 0 and 2. So this thing, we have 2, and then 0, and anything in between. And why is this not a cut? Because it doesn't satisfy the second property. For instance, notice 1 is in it, because 1 is in S, and let's say -1 is less than 1. But -1 is not in S. So you see, S does not contain all the numbers less than 1. And that's why the second property fails. And similarly, anything of the form greater than is generally not a cut. So also S is, let's say, the rational numbers greater than 2 is not a cut. So again, those things, so this is 2. And this is all the elements in S, because again, for instance, 3 is in S. Again, because 3 is in S, and let's say -1 is less than 3, but -1 is not in S. So again, you have an element in S, a rational number less than it, but that rational number is supposed to be in S as well, but it's not. Okay, that's good, and generally, as I said, stuff with less than or equal signs are also not in S, because generally they have a maximum, which we do not want. For instance, if you choose S to be all the rational numbers less than or equal to 1/2, this does not have, this is not a cut. Why? Simply because, remember, what's the condition? So for any element in S, there's something greater than it, but there's nothing greater than 1/2. So because R equals 1/2 is in S, but there is no S greater than that. No S in S with S greater than 1/2. So we're supposed to find some element that's bigger than it, but that's not true. And again, what makes this false is basically this less than or equal sign. So generally speaking, again, a cut is just sort of a half infinite interval, more or less, with like less than signs. And in fact, let me give you now a couple of examples of cuts. So this thing. Again, for instance, the first that I talked about, so now actual examples. Again, the first set I talked about, which remember was something like 1 minus 2, and then 4. I forgot which numbers I put, but something like that. And then 1.41. Again, essentially the numbers that are less than square root of 2. This is a cut, and that cut we call square root of 2. Okay, that's from before. But of course, this is not very satisfying. How is there a better way to define square root of 2? Well, in this case, yes. But it's a bit trickier, so let's actually define cube root of 2 first. That's a bit easier. So take the set of rational numbers whose cube is less than 2. This, you can show that it's a cut, and I think on your homework you do that. So this is a cut, and that's what we define to be cube root of 2. Now, again, some specific set of rational numbers, that's what cube root of 2 is. And you might guess, well, can't we just do the same for square root? Unfortunately not, because this is not a cut. Because essentially what is this? Is the interval minus square root of 2 comma square root of 2. Okay, so this is S in some sense. Okay. But what's the issue? For instance, 1 is in S, because 1 squared is less than 2, and let's say minus 3 is less than 1, but minus 3 is not in S. You see, the number 1 is in S, but not anything smaller than 1 is in S. For instance, minus 3. It's smaller than 1, but it's supposed to be in S, but it's not. On the other hand, the nice thing is, well, you can actually modify it if you just adjoin the interval minus infinity 0. So let S then be the following. So consider all the rational numbers such that R is less than or equal to 0, and adjoin the set of rational numbers. So take the union of the rational numbers whose square is less than 2. So again, picture-wise, what does that look like? We have our set from before, the set of rational numbers less than 2, but also you're unioning it with this set, the set of numbers less than or equal to 2. Then if you take the union, you actually get this whole set here that contains 0. And this is a cut, and that's what we call square root of 2. And again, all these fun things you will prove on your homework. So is a cut. Called square root of 2. And again, you can not every real number you can define with like polynomial equations like pi. You cannot define it that way, but again, you can think again as pi being the set of all rational numbers again that are less than pi in some sense. So that's set 3.1, 3.14, and then 2, 0, minus 2, etc., etc. Okay, good. And now that we define what the cut is, let's figure out how to do operations of cuts. Because remember, for real numbers, we can add and multiply them. And the question is, can you do this for cuts? Of course, because cuts are real numbers. But let's see how to do this. And it turns out the definition, at least for addition, is very beautiful and straightforward. So in other words, if S and T are cuts, then what is S plus T? Very easy. You just add any element in S with any element of T. So it's just S plus T, where S is in S and T is in T. Of course, we can define whatever we want. The whole point is it has to be powerful. So, but indeed it is, because it turns out if you add 2 cuts, you still get a cut. So fact, and I think that's also on your homework, beautiful. So if S and T are cuts, then so is S plus T. Okay, very good. And well, you might guess, oh, if addition is so nice, I bet multiplication is nice too. Unfortunately not, because you cannot just define ST to be ST such that S is in S and T is in T. I mean, you can do whatever you want, it's math, right? But the whole point is, though, if you define it that way, then ST isn't always a cut. And in fact, I believe, it's not always that way, but I won't do this in this video, but if you want, there is a more complicated way of multiplying cuts. And I invite you to look at this beautiful other yellow book where the author defines cuts, a multiplication of cuts. But just know there is a way of multiplying cuts. And the nice thing is, here's why this is so cool. So fact, Again, first of all, what is the real numbers? So the real numbers is just the set of all the cuts. Technically speaking, it might not be a set, it might be a class. So set of all cuts, S. And here's a beautiful fact. With addition and multiplication as above, it turns out R becomes a field. So compared to what I said in section 3. And not only that, it's an ordered field with a beautiful order it's so beautiful you won't believe it's true, but it is true. So definition, how would we order two real numbers? Well, S is less than or equal to T if and only if S is a subset of T. For instance, I'm claiming that 1 star is less than or equal to 2 star, and that's basically because 1 star is a subset of 2 star. Might not seem obvious, but let me draw a picture. So this is 1 star. Again, all the rational numbers less than or equal to 1. And this is 2 star. All the rational numbers less than or equal to 2. And well, if you're less than 1, you're definitely less than 2. That's why this is actually a subset of this. And what's beautiful about this is with this very simple ordering, R becomes an ordered field. So, fact, with less than or equal as above, R is an ordered field. And not only that, I don't know if you remember, but for every rational number, we can associate a rational cut. So given A, we can associate A star, again, which is a cut. So again, given 1, we can associate 1 star. And with this association, we can actually say that Q is a subset of R. In other words, given any rational number, we can construct a real number, but not every real number is of this form. And so, for instance, let me draw a picture just to clarify. So we have here the set of real numbers, so R, which is all cuts, and then we have the rational cuts, okay, which is again 1 star, a 2 star, or 1/2 star. And again, every rational cut is a cut, but not every cut is a rational cut, which, for instance, the set of R, such that R cubed is less than 2, that's not a rational cut, because it corresponds to cube root of 2, which is not rational. And that's why, you see, we can really think of the rational numbers as a subset of the real numbers, just by thinking about rational cuts. And therefore, what do we have? We have that the real numbers form an ordered field that has sort of Q as a subset in some sense. And not only that, and this is what we'll prove next time, R actually has the least upper bound property. So therefore, fact, with this definition of R satisfies the least upper bound property. Namely, any subset of R that's bounded from above has a least upper bound. So supremum exists. And you'll see what the reason we define cuts is to make this very elegant. All right, thank you. That's all for now.